Welcome class to the third lecture for Module 5. Today I'll introduce the one-way within groups ANOVA and then also explain how it differs from the between groups ANOVA when it comes to the analysis. Now we've already talked about that we use an F-test whenever we have more than two groups, and we demonstrated that with a between groups ANOVA already. Now we're going to talk about a within groups ANOVA. Now the basic difference between these two ANOVA designs is that the between groups ANOVA is what we call a between groups design, and the within groups ANOVA is what we call a within groups design. In other words, the within groups ANOVA will be very similar to a paired sample t-test in that our observations are being measured more than once. Now let's go ahead and use the same example that we used for the one-way between groups ANOVA, except now let's change it up just a little bit so that each of our participants receive every condition or every level of the independent variable. So if you remember back from the one-way between groups ANOVA lecture, we talked about having an independent variable of drug condition, where either patients received no drug, they received a placebo, or they received a new drug that relieves pain. And so the dependent variable here is the pain experience. So we measure the pain they experience after being in one of these three conditions. Now in that one-way between groups ANOVA, each patient was in one and only one of those conditions, either no drug, placebo, or the new drug. However, with a within groups ANOVA, we may want to have the same patients or the same participants experience all three levels of the drug. And the reason why we might do that is because people have different tolerances to pain. And so there are individual differences among patients. And so if we can capture that individual difference among the patients, then we can remove it from our analysis. And so with a one-way within groups ANOVA, we can use the example of drug condition where each patient gets a measure of pain without any type of medication. Then we may give them a placebo and measure their pain to see if there's any psychological effects of receiving something, even though it's not the drug or has a drug effect, receiving something. And then we might then have the same participants get the new drug treatment that reduces pain or should reduce pain, and then we'll get a measure of pain experienced. And so in this case, each participant or each patient experiences all three levels of the independent variable, in this case the drug conditions. Whenever we conduct a research study, we always have to be concerned with human biases or human errors that creep into our research design. One such error is called the order effect. So the order of presentation of the levels of our independent variable matter when it comes to the ratings that participants provide. So for example, if we were to give the new drug to patients and then measure their pain, and then give the placebo and measure their pain again, we have to be concerned with a carryover effect. In other words, the medicinal qualities of the new drug may carry over into the placebo condition. And so we have to be concerned about the order in which we present our levels of an independent variable. To demonstrate the order effect, let's use our example from class when we conducted a between groups ANOVA. So if you remember, in class, each participant saw one and only one of the body types. But let's say we wanted to have participants view all three of the body types to account for the fact that people differ from each other. And so maybe we show the mesomorph body type first to everybody, and we get an overall average or rating of 5 on our 1 to 7 scale, where higher numbers means more perceived attractiveness. Now because it's the first body type that we might see, our human tendency is to not rate towards the extremes of our rating, so we're less likely to rate a 7 or a 1, and we're more likely to rate someplace in between the extremes on our scale. And so maybe overall we get an average of 5. Because participants didn't know what to expect after the first image, they rated the mesomorph body type likely in the middle of the scale rather than at the extremes. So then we show them the second picture, maybe it's an endomorph body type. And in comparison to the mesomorph body type, they might rate that endomorph body type lower than if they had seen that endomorph body type first rather than the mesomorph body type. And so maybe on average they rate this endomorph body type a 2 in comparison to the image that they saw first, which is the muscular mesomorph body type. Now if we had shown the endomorph body type first, again, participants would have rated on average more towards the middle of the scale rather than the extremes. Rather than a 1 or a 7, they're more likely to rate around a 3, 4, or 5. And so if we had shown the endomorph body type first, they may have rated that endomorph body type around an average of 3. Again, because they didn't know what to expect with the second image, participants were more likely to rate in the middle of the scale. So then we show them the second image. It's the muscular build, it's the mesomorph body type. And our natural inclination as humans is to compare the current image with the previous image. And because of the stark contrast, the participants are more likely to use one of the extreme ends of the scale. In this particular case, they would probably rate the mesomorph body type higher than they would had they seen that mesomorph body type, that muscular build, first rather than second. And so maybe now they report the rating of attractiveness to be around a 7 on average, rather than the 5 that we would have saw had they seen the muscular build first rather than second. The order of the body type image changed the perceived attractiveness of the body type. And so if the endomorph body type was presented first, then it received a rating of 3, but if it was presented second, it received a rating of 2. The mesomorph body type, or the muscular build, if presented first, received a rating of 5, but if it was displayed second, it received a rating of 7. And so if the numbers change, then there must be some error involved in the analyses. And so that's what the order effect is, that the order of the presentation can change the rating provided by participants. Because as researchers we know that the order of presentation matters when it comes to within groups designs, we want to make sure that we don't present the same order to all of our participants. So the best way to combat the order effect, or the error due to an order effect, is to randomize the order of presentation. So some participants, they'll receive the endomorph body type first, others will see the mesomorph body type first, and over many observations we'll be able to average out the error in the order of the presentation. So each participant may have a different presentation order than other participants in the study, and that helps us to reduce the order effect. Now realize that the order effect, or the error or the bias, is still in the individual values, but because we're looking at a group or a sample of individuals, we're able to average out that error over many observations or over many participants. Now as a reminder, we're still doing an F-test, so we'll still use the F distribution. Remember, the F distribution is different from our T and our Z distributions because it is a skewed distribution. It's a positively skewed distribution, and it's centered at 1 rather than centered at 0. And the reason why it's positive is because we are using squared values. Essentially, the F distribution is the T distribution squared. And so all those negative T statistics end up turning into positive F statistics. Now the assumptions for within group ANOVA are going to be very similar to a between groups ANOVA. In fact, because it's a within groups design, the assumptions for a within groups ANOVA is going to be the same as a paired sample t-test, except now you have more groups. So if you remember with the paired sample t-test, our observations are being measured more than once. Well, that's the same thing with a within groups ANOVA. Our observations are being measured more than once as well. We just have more groups, and so the assumptions are all going to be the same. So if you know your assumptions for a paired sample t-test, you know your assumptions for within groups ANOVA. Now because the assumptions for within groups ANOVA are exactly the same as a paired sample t-test, I won't spend the time talking about each assumption individually, but I do want to talk about the very last assumption briefly. So the last assumption is that participants experience all levels of the independent variable. So when we say participants, what we really mean is observations, and so it doesn't always have to be individual people. It can be groups as well. Something like siblings who share a genetic trait. If we have 3 siblings in a family, then we can still do a within groups ANOVA. So here might be a basic within groups design. Notice our level of observations are individual people, and so we have Samantha, Greg, Hannah, and George. And we're going to use our example of pain relief based on the type of drug treatment. And so we might have Samantha here, and we get a measurement of Samantha without any type of of treatment. That's the none condition. And then we might get a measurement of her pain with a placebo, and then also with a new drug. And so Samantha is being measured 3 times, once for every level of the independent variable. But what if our level of observations wasn't necessarily individuals, maybe it was groups? And so here we may have siblings in a family. So we have brothers and sisters in a family, and we may want to measure the effectiveness of our drug types. And so here, because there's a genetic component to pain tolerance, we can get members of the same family and give each of them a different level of the independent variable. And because they share a particular genetic trait, they are dependent upon each other based on their genetics, then we can reduce some of the individual differences due to non-genetic factors. So we can still do a within groups design for our ANOVA as long as our level of observation, in this case siblings or family group members, share something in common. So in this case it would be their genetics. So we might have Samantha, Alex, and Travis all being brothers and sisters within the same family. And so we can still do within groups design as long as our level of analysis in this case are family members. So again, in this case we can still do within groups ANOVA as long as each row that you see here in our presentation are members of the same family. And so we might have Greg, John, and Susan, all brothers and sisters to each other. Hannah, Karen, Ginny come from a different family, but they're all siblings as well. And George, Joy, and Gerald, again from a different family, but again they're all siblings. And so as long as they share that genetic component, we can still do a within groups design, even though they're individuals being tested within each level of the independent variable. They still have a shared genetic component that we can use to reduce individual differences. So let's take a moment and talk about what differs between a within groups ANOVA and a between groups ANOVA when it comes to the actual data analysis. Because it's easier to use a source table when conducting an F-test, we'll still do that with a within groups ANOVA, but notice how the source table has changed. We have added a row to the source table. The row that we add is a row called subjects. Essentially what this row does in our F-test is it allows us to test if our participants are different from each other. So remember, we're trying to remove the fact that people differ. And so if we can measure how much people differ from each other, then we can remove it from our analysis. And so essentially that's what we're doing with a within groups ANOVA. We're getting a measurement of how people differ from each other. And then we're going to remove that variability, or the fact that people differ, from our analysis. And that's what this subjects line gives us in the ANOVA source table. Another difference between a within groups ANOVA and a between groups ANOVA is the calculation of an effect size. So after we do our hypothesis test for the F-test, we then want to get an effect size so that we can get an unbiased measure that's not affected by sample size nor by probability. And so we'll still use our R² formula, but notice that in the denominator we are going to subtract out the variability due to subjects, or the sum of squares for subjects. So essentially what we're doing is we're removing individual differences from our analysis. So we're removing the fact that people differ from each other. And that allows us to see how much variability is due to our independent variable, rather due to our independent variable and individual differences. So we'll remove the individual differences, and that will give us a more accurate effect size. As a result, our interpretation for an effect size will change just slightly. So we're still talking about the percent of variability of our dependent variable due to the levels of our independent variable. However, we're going to add the statement at the very end that says when individual differences are removed. So again, remember, in our formula, we're taking the sum of squares for subjects and removing it from the total variability. In other words, we're subtracting out the fact that people differ from each other. So our effect size will now be the percent of variability. If we use our example of pain relief and drug type, we'll say the percent of variability of pain experienced among individual patients can be accounted for by the drug type when individual differences are removed. So it's still at the individual level, but we're removing the error due to individuals or due to subjects or participants. Alright, so that's about it as far as what changes between a within groups and a between groups ANOVA. So we'll come to class and we'll go through an example of a hypothesis test, and then we'll continue on the review day to go through another example. Alright, I hope you have a good day, and I'll see you in class.